Now, I talked about being able to see photons and electrons and muons and the tiniest particles that exist with CMOS, which is this right here, a cell phone. This goes back to 2012. This laser, this cell phone, did these particles. Could see these particles using a little tuned Venturi developed by Rod Warren in Australia. And when I presented this to CERN and Fermilab and all of them, they literally laughed at me and literally called me names. But I ended up going to the University of Geneva for particle physics, and I showed them this stuff, and the same thing happened. We went back and forth, and finally they agreed, wow, this is amazing. And guess what? Everybody agrees now. All right, listen to this now very carefully, because they would not accept this at all. I was really assaulted for saying these were pictures of photons. I asked, can CMOS see muons and electrons? Yes. CMOS image sensors can detect muons and electrons, and they're the same thing. This was it right here. This is the one that did it. From 2012, a Galaxy S3. CMOS sensors, particularly active pixel sensors, commonly used in digital cameras, which is the cell phones, are sensitive to charged particles like muons and electrons. And they pick them up as like almost like a movie. I'll show you. When a charged particle such as a muon or electron passes through the sensitive region of the CMOS sensor, which is typically a silicon epitaxial layer, it creates electron hole pairs through ionization. So as it comes through, it's clicking off ions, which are dipoles. Dipole electrons, and these little electron hole pairs are then collected, generating an electrical signal that is converted into a pixel value appearing as a bright spot or track on the resulting image. And we see them as a whole array of particles looking like it, but I can see that they are like almost like pictures looking. Well, I'll show it to you, and you make your own decision. That's what I'm picking up. Now, muon detection from CMOS. Muons, high-energy particles produced by cosmic rays and by our experiment, and by CERN and Fermilab, interacting with the atmosphere, can be detected by CMOS sensors, even in ordinary digital cameras. Yes, that's what I told them. And boy, I'll tell you, we had it all. And then they upgraded CERN to use these. I don't know what they did with Fermilab. Fermilab was, and they still have me blocked. It was a very nasty interaction with Fermilab, and I told, well, I'm not going to get it. We had a hell of a battle, I'm going to tell you that right now. And all I wanted them to do was to examine what I had to say, and it was refused. These are the Fermilab particles, and they are identical same particles. We use light. We can see them with CMOS, because you can see photons, and you can see the electrons. You can see dark matter, but you could, and these are the particles. Now, when I say we saw them like a movie, you can see them moving. You see this? This is not just, this is a picture of it all happened at the same time. Let me show you, well, hold on a second. All right, so you know that these particles, this is all valid stuff now. They can't dismiss this anymore. They know that the CMOS works very well to see this stuff. And this is what happened. This is pulsed red laser just starting to accelerate. That's the full acceleration, and you can't miss it. It's just unmissable. That's accelerating, and when it hits the Venturi, it explodes. The black didn't go through, but the white did. The white separated, and they're doing this now at CERN and the rest of them. They're trying. I don't know how. They want to use these gigantic machines they spend a ton of money for, and they want to hit a big particle and then make it end up being these particles. Why don't you start with these particles? That's my question to them. Why don't you start down here where we did? You want to end up with the white being separated. That's electricity. If you can create free electricity, we're golden, and I think we can. Because right there, we separated. We did nothing other than shoot the laser here with a Venturi, forcing the fields to crush, just like they do head on. We forced them to in here, and they can't get back out. Theirs, they go like this, and they go like that, and they go like this, and about every billion times they hit one head on. And I mean, I'm serious, about every billion or trillion times. They are, bam, but they just go this way and this way. The fields bounce. But if sometimes they hit head on. We have head on every single time. And then they come out the other side with these Higgs fields. This is blue coming in really hot, slowing down. You can see it slows down. You can see we speeded it up. You can see light is a particle. Let me show you that a little better. And nobody knows about this particle whatsoever except me. That is one of the most unusual particles. Well, it's the only one I've ever found, and most all of them are like this. They don't. I know what happened here. After 3.5 years, I have figured out what happened. And I'd love to talk to some physicists. I have every right to speak about this. CMOS sees these things we have done. We have found the particles at FERMILAB and CERN. I can show the light here coming through, just through the atmosphere, and interacting with all the other particles that have fields on their own. Every particle there is, every gas, every bit of moisture, every bit of anything, every dust, has glowy particles that surround the core of that atom. All right, because almost everything is atomic. We're in the subatomic realm, which is light. But when you're in particles that are just floating in the air, they're fully atoms. They're not light. So we're way down. We're 1,000 times smaller than atoms. And we're coming through here, pulsed. The head of the wave is pushing everybody out of the way. Get out of the way, get out of the way. It's push to shove. They're pushing to shoving. But these guys got to get out of the way because this is just going to keep coming. That is not going to stop. So what happens after this? Here's what happens. It's approaching the Venturi. The Venturi is right there. And that Venturi is nothing more than, well, it's actually rounded. And there's one in the middle too. There's some of them have. Rod did just a fabulous job at experimentation. He was trying to start with a double slit, which you would have, and he used nails. He put a nail here, and a nail here, and then he shot the laser in, and it forced exactly the same thing as this. And this may even be a triple nail. I'm not sure, but he had 2 and he had 3 and. We had all kinds of things we were doing. And he was going through glass and all kinds of stuff. But you can see the wave has accelerated. I mean, it's just nobody in their right mind can miss this. And at this point, the photon shows up because of the back push. It's called reverse electromotive force. Electron pushing back. There's huge field waves all the way back through here pushing back against this. So when that particle hit right about here, just as all of these that are coming, you don't even see them, but they're all over coming down. But when it hit here, it's just they think they hit a wall. They think they hit a wall because this is pushing back so hard. And we can see this right way over here. You see that? You see those reverse waves? You see how glowy they are? And back right into those, they're hitting particles all over the place and turning them on. That's reverse, huge amounts of energy. An absolutely stunning quantity of energy that you're seeing there. Stunning amount of energy. Just as it states in the manual at CERN, and FERMILAB, Lawrence Livermore, all the rest of them. Let me show you. Okay, my friends, I am going to show you the dipole electron flood theory just can't be denied. And there are some things that are just ununderstood, like that light does have weight, and the dark matter literally makes up everything and is part of light. And dark matter attracts. It doesn't repel each other. They say like forces repel and opposite forces attract. Well, it's dark matter attracts it to itself. White light, totally the opposite. White wants to be with the black, yes, but white hates the other white, and black loves the other black, and black and white love each other. That's the key. It's not always opposite forces repel. Attract, and like forces repel. Like force of the dark matter creates a black hole. Okay, I'm going to show you that the things we're thinking just aren't right. I asked AI, AI gives you all the current thinking, who's thinking what. And I said, is the fact that the speed of light is consistent and constant based on the fact that photons have no mass? Excellent question. Yes. Well, photons do have mass, as I will prove to you. The fact that photons have no rest mass. Now, here's where they're trying to hedge their bets here. They have no rest mass. In other words, they're just sitting there. They don't have any mass. That's not true. They weigh 0.0008545, something like that, atomic mass units. 1,839 of them together make the weight of one proton, which is one atomic mass unit. So they do have a mass resting or in flight. When they interact with something else, then the mass goes totally different. It becomes it's an impact at that point. Then it has a lot more mass because the field is interacting with another field. Different story. So, like Einstein called it general and special relativity. Well, we can call it that. If it's just sitting there, it just weighs a certain amount according to the gravity. That's all. How much gravity there is determines how much it weighs. Simple as that. When they're out in the space station, they're just floating around. There's not enough gravity to pull them down. But there is some gravity, and I can show you that in the pictures from space where they did an experiment in a vacuum chamber and they could see a black hole. I paid very close attention to that, and I actually they didn't correspond back, but I contacted the Russians and I showed them our experiments with the light and seeing these particles that they were seeing and trying to understand. Anyway, it was a long time ago. It's 10, 11, 12 years ago. So anyway, it says the shorter answer, yes. The fact that photons have no rest mass directly tied to why they always travel at the speed of light in a vacuum. First of all, there is no vacuum in space. There's no vacuum. It would be insane to think there's a vacuum. The Webb telescope is all based on the fact that light will never slow down, and that's just totally wrong. All right, they're saying light never slows down, and that's why relatively modern physics works consistently. No, light does slow down. Modern physics just doesn't work at all. I guess this space is a vacuum. Yes, space is a vacuum, but not a perfect one. It's not a vacuum at all. What does a vacuum mean in space? Area with very few particles. It doesn't matter. They're passing through them. I'm going to show you pictures of fields, if I haven't, of what's in space. It's just nonsense to think that there's no push to shove here. All right, this is the guy I interacted with, Don Lincoln, senior physicist at FERMILAB, well-known science communicator, has indeed used the metaphor I just described, which is this. Did Don Lincoln from FERMILAB say that space is filled with a quantum foam of particles that blink on and off like bubbles on a root beer? That's space. Is it filled with all particles? Yes. Don Lincoln has said that, a well-known communicator. He explained quantum vacuum and quantum foam, which they blink on and off because they're being hit by particles that are moving fast. These are the cosmic microwave background. They just hit and they blip, 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 blip. And that's what he says, bubbles in boiling water, foam on root beer. The vacuum isn't smooth, it's frothy. And it's frothy because certain areas are going to be heavily particulated and be turning on and off a lot. They glow because there's so many interactions. At other places they're going to be pretty sparse. It will be frothy. He's right about this. What is the quantum foam? It's the particles in space. It's the cosmic microwave background and all the other light particles, which are particles which have weight flowing through and banging into them. Okay, so as Don Lincoln says, space is a quantum soup. Here's what they come up with their little diagrams. Ever since I've been showing the dipole electron flood theory, I'm seeing these things from the physicists. They're trying to sneak their way in, basically, and they're showing how these dipoles, a white one and a black one, in space entangle with each other. Well, guess what? We can see that much better, which is what I have been showing, is the much better shots like that. All right, these are dipoles, and that is a strange one. And this stuff here, I can't explain it. But I do know what these are. These are magnetic fields, and those fields interact with particles that are flowing through them. They don't, this is not empty space. This is saturated, just like Don Lincoln said, with quantum foam. And they blink on and off as they hit particles that are coming at them or they're banging into. And sooner or later they slow down to a point where they're just barely moving. They call it the cosmic microwave, which means way low particles spectrum, the cosmic microwave background. It's just laying around out there, and as they get hit, they blink on and off like the head of the root beer. Just as Don Lincoln from FERMILAB said. Here's the evidence to support those claims that Don Lincoln made. And here's another one. And these are the fields. Now, I showed you what they are claiming. This is what is out there. And I have my idea what planet this is. I'll explain that later. This is our moon. And this blue shift. Explain that. Now, we can see all this stuff with CMOS. They know this. They understand this. Now, this is what CMOS is made for, is to see frequencies like this and turn them into images like that. Now, you can see they're dipoles. There's no question whatsoever. Literally everything is a dipole. Sometimes you don't see it completely as a dipole. But in space, as they spin and create these glowing fields or energetic fields, let's put it that way. And you can see them with CMOS. CMOS is designed to pick up these flutters that are coming through its structural material. They're the complementary metal oxide semiconductor silicates. And it does a fabulous job. And we've been doing this since 2012, 13, right in that area. And it's undeniable, really, that the particles in space are interacting with these fields. They cannot not interact with these fields. They are flowing through there. Not only that, there's so much dust out there, and every particle of light is a particle. I have shown you the particles of light. They are particles of that. There is no doubt whatsoever they are particles. And here they are right there. And under my theory, which is correct, as a matter of fact, these are the only two particles that exist, and that is the only one that has the weight, and that's dark matter. And it's inside of the glowy parts, which is this, because they want to attract to that so bad that they'll surround that thing. And you won't see it. Every time you look at it, it just bounces back at you. It's inside the glowy part that we look at. So everything we're looking at here is coated with these. These are not on top. Those are underneath. That's why we've never seen them. But when you split the light, because they're in light too, but light's too small, you know, to see, unless you use the CMOS, then you can see it. And these are those particles. These are those particles. All right, that's light. And everything there is made of light. And they have weight. If you shine that on something, it'll get warmer. All right? If you shine light on something, usually it gets warmer. If it's real reflective, it won't absorb any light. But when it's dark stuff absorbs the light. All right? And it gets warmer. And when it gets warmer, do you think it floats up in the air? No, it sinks because it weighs more. It's almost unmeasurable, but trust me, I worked with the weights and measures, and you have to have the temperature of the weights at the same temperature at the same time before you can calibrate them. Because the heat adds weight. You see, there it is right there. This is from 2013 once again. Empty space isn't empty. Quantum foam by Don Lincoln at FERMILAB. That's what a quantum empty space isn't empty. It's filled with these tiny little bubbles that blink on and off because they're particles that have an energetic field surrounding them, but they're basically not doing anything. They're just hanging around out there. And when they get hit by a piece of light, blink, 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 they blink on and off. And that's the cosmic microwave background he's talking about, quantum foam. Okay, my wonderful friends, we are going to be going through particle physics again today. They're getting closer and closer to realizing that dipole electron flood theory is the theory that works. And they're talking about they might have discovered this new force of nature inside of atoms. It goes back to like 1930 or something. They're looking at a particle that was talked about way back then, and they say now they call it I can't remember what they hadrons. Hold on a second. Okay, my friend, you're going to think this is complicated. It is so uncomplicated. It's unbelievable. They're talking about the fifth force of nature may have been discovered inside atoms. It's been hiding there right along. They're calling it a pion. This is what they're saying right now, that there might well be forces hidden deep inside the atoms with tiny storms of particle dynamics that have been simply too subtle to easily detect. Well, I think we found them, and I'll show you this. But this is what they're saying. As handy as the standard model of physics is, which explains atoms, as handy as it is at explaining cosmic and quantum phenomena, glaring gaps leave physicists scratching their heads because it's just not right. And it was by Einstein, so everybody, oh, Einstein, yeah. Well, Einstein was just not right about virtually anything. Dark matter remains elusive. Not really. For example, nobody knows why one kind of matter came to dominate after the Big Bang. We're going to discuss that. Dark matter is what everything that has mass is made out of, primarily is dark matter. That's the only thing that has mass. Gravity is the most questionable member of the force family. Gravity is strictly because there's so much dark matter in the Earth, it attracts the white matter, which is attached to all dark matter, so it is attracted to the Earth, which has a significant amount of more dark matter. Lacking a quantum theory to explain its behavior. No, I can explain it quite well, and this is, I explained to you, this is just not correct at all. There's not all these particles whatsoever. There's only two particles. There's a black one and a white one. I'll show you those in a minute. Now they're talking about a Yukawa particle, hypothesized mediator of possible forces within the core of atoms. Well, let me tell you something. If you look into that particle, if you forget about it, it's just a big bunch of nonsense, to be perfectly honest. Okay, this is the Yukawa interaction, and it's named after this guy, Hideki Yukawa. It's an interaction between particles according to these potentials, specifically between a scalar field, a pseudoscalar field, and a Dirac field. The Dirac is what I work in, the Dirac area. And then they go on to talk about hadrons, which there are no hadrons. And then they go on nucleons and pions and all these pseudo-scalar mesons, and then they go into just the most nonsense of all this stuff. I did all this kind of stuff years and years ago. It's just total nonsense. And when I said you just guys are making up things to try to justify the things that you talk about, who the hell is ever going to do this? Look at this. Who's going to do that? But they're talking about Majorna spinners and same mass broken out in two chiral Majorna spinners and on and on and on. Well, let me show you something. I can show you dark matter. I can show you light exceeding the speed of light. I can show you photons. And I can easily explain dark matter, mass, gravity, and energy. It's quite simple. Okay, my friends, this is the Yukawa interaction, which just is not correct. And it's based on flawed physics, which the biggest flaw in the whole thing is this is massless. Particles such as photons are stable. Massless. They're not massless. They are stable. Those are light. They bounce because they have a surrounding field surrounding the core particle, which is the photon. It's two gluons back to back. All of these things they're throwing on here, they talking about gluons, I agree with that. But there's no such thing as a massless photon. And they're calculating everything based on this massless photon. It's just not massless. All of this stuff is absolute, I got to be honest with you, it's just nonsense. And all of that stuff, if you want to read through this and try to figure out what all that stuff means, and if it has any meaning at all, which it does not, good for you. That's all I could say. But they're talking about the Majorna field. They're talking about Diracs. They're talking about the photons. You know, but they're just starting from a wrong assumption that light has no mass. It certainly absolutely has a mass. And that is where the dark matter exists, is inside of light. Okay, my friends, the truth is, since I introduced the dipole electron flood theory, it's being written up in physics worldwide now. And they're trying to come up with some kind of a counter against my theory, and there's just no way to counter it because it's true. Now they're talking about a fifth force discovered inside atoms, may have been discovered. Well, maybe. And they're talking about the standard model of physics just is not right. It explains cosmic and quantum phenomena, and it does not. The glaring gaps that leave physicists scratching their heads. It's not right. Dark matter, I have no idea about it. It remains elusive, for example. Plus, nobody knows one kind of matter came to dominate after the Big Bang. They say the dark matter dominates the universe. The dark matter is the only thing that has mass. The energy does not have mass. I can't explain it, to be honest with you, but the energy does not have mass. If you charge your car up if it's an electric car, and it's completely dead, there's no charge in it whatsoever, it weighs 4,000 pounds, you charge it up full where you can drive 500 miles, it still only weighs the same. It does not add any weight. You drive it all day long, you come back and it's empty again, it still weighs the same amount. You fill it up with juice, it still weighs the same amount. There is no weight to pure electricity, which is what it runs on. The other side of electricity is the dark matter, and that's where the weight sits. Let me explain it to you, and I can actually show it to you in a nuclear bomb blast. But all of this stuff is just not true. It's just not right. And then they come up with this Yukawa particle, hypothesized as a mediator. Well, this isn't right either. This is based on the fact that photons have no mass. Okay, my friends, I'm just going to tell you right now, they're trying to ease into dipole electron flood theory by now showing these polar particles. They're calling, I'll show you the name in a minute, but dipoles are the nature of everything, and there's only two particles that exist. There's black ones and then there's white ones. Now, the reason we see these different colors is because of how far away they are from the attractor, which is the dark matter. That's dark matter. And it attracts the white matter viciously. That's what electricity is. The white goes to the dark. The dark has all the mass. The white has virtually no mass whatsoever that we can find, or Fermilab, or CERN. There is no mass. So therefore, they think a photon has no mass whatsoever, which is wrong. A photon includes some of this black. And here's what photons are. First of all, these are the only two particles that exist. Is the white glowy part has no weight, and the dark heavy part has all the weight, and the two of them together make a dirac, which now they're going to call this particle. And they also call them gluons. I agree with that. They don't lay sideways. They always lay polar towards the Earth. And this is what a photon is. It's two gluons back to back. Simple as that. All these other color variations are how close the particles are to the black. The closer it is, the brighter their glow. Because, in other words, to rip it away, it takes a lot more energy if it's hugged right up here. If it's out in the periphery, it takes less. And if it's way out, it's just, the particles just basically leave easily. But that's a whole other issue. But everything has to change. Chemistry has to change. Space, time, distances. Redshift doesn't shift red. It's just light slowing down. And I have shown all of these things, and I'll show them to you right now again. But these are the only two particles that exist. Normally, they're going to be attached together like this if they are simply heat, which is just an extra dipole. It just has nobody to attach to, so it moves in as heat. And then eventually there'll be enough white particles like in the atmosphere that they will have to discharge to ground. These are ground. Earth is ground. Everything that has mass, including us, includes dark matter. That's where the dark matter is. They say, where is it? We can't find it. Well, it's right there. It's light is half dark matter. That's the only part that has mass. And light does have mass. That particle right there, my friend, has mass. Absolutely zero question about it. And this is Fermilab. And certainly they see the same particles. These are the two smallest particles that they can find that exist. It's the same with us. But we started with light. They started with huge particles. So they had to dig through, and they keep seeing these, and they know that they're there. They just don't understand it. We understand it because they're part of light. And that's from Fermilab. And Don Lincoln, Fermilab, says this has all the weight, and it's a fixed particle. Never changes size. It has all the weight. This one can get big and get small, and it has no weight. It just has a field. And that's exactly the way he explains it. And that is exactly what we found in our experiments. Those two particles attached together. It's a gluon. It's what it is, a gluon. Now, this is the colorized spectroscopy look at this. It's a photon. And that came from a red laser. And these two are the same two he has here. So you have two bar magnets, basically, which makes up a photon, which has a field surrounding the whole thing. If it was just one of those, it will work its way into some other matter and become heat, because it will want to be attracted by a coldness, which is the more dark. So it will want to attract to that. But if at some point this becomes, warmer, it will expel it. It'll push it out. It'll say, no, we got enough. It's got too hot in here. Go. And if it's cold, and out here it's warm, it'll say, hey, you got any extra warm, guys? I say, yeah, come on. And they come in, and it warms up that thing. Now, why I can say this has weight, and there's no question whatsoever, every dipole has weight. When I was in electronics, selling electronic equipment, one of the things was weighing scales for commercial use. you had to have the weights at the exact same temperature as the scale calibration unit. What I mean by that is if you took the weights up there and they were cold, and you put them, and say they were 40 degrees, and you put them in a 70-degree room, which the calibration equipment is at 70 degrees, you put that 40-degree weight on there and you adjust it for 1 pound, it's not going to be correct. It's not going to be correct. It's going to be cold, and the other part is warm. They have two different potentials of darkness inside of them. Because don't forget, like I said, cold wants heat to come to it. Heat wants cold to come to it. They want to resolve each other to become ambient, the same temperature, and that's what we had to do, is leave the weights overnight so that they became the same temperature as the room. Then they could calibrate them. Otherwise, you couldn't calibrate them. But what they were missing was when the guys would go out on the street, they could bring them in cold, and the room would be 70 degrees. So, so the calibration, you know what I mean? But it was so minor. It was such a tiny amount because you're adding electrons. All right, when something gets warm, it doesn't always lift up because it's not gases. If something solid gets warmer, it gets heavier. And I know that there's no question about it. So if something gains heat and is a solid, it will gain weight. That means heat has weight. Heat to us is a dipole. Well, heat to anybody. And two dipoles back to back make a photon. We accelerated light. I have some papers here. I have to validate my experiences and my work that I did since 1968. Actually earlier than that, but 1968 I really kicked off because that's when I went in the Army into nuclear stuff. And I was up at Fort Richardson for, you know, Nike Hercules missiles and, you know, maintenance of the sites and so forth. Anyway, this was my original work. All right, intermolecular forces. There's only two types, and they're both dipoles. There's polar ones and there's non-polar ones. And this is this goes a long time ago, and this was my ending result was transfer of energy is from light into atomic vapor. That's atomic vapor. That is atomic vapor. Light is a vapor. When it condenses, it becomes atoms. It's atomic vapor. It's just like mist. When it condenses, it becomes water. No difference whatsoever, basically. And just to tell you, I'm going to show you the calculations they want you to do to verify this, whatever particle they're calling it now. I know how they work this stuff. They just make it into a big ball of nonsense. I did all this. It was just the biggest waste of time I ever used in my life. It's just ridiculous. But I did it just to prove that it wasn't right. I knew it wasn't right from the beginning. Because you can't have one big solid thing that has a charge of 5 and it's like 1,000 sizes, and then you have a couple little electrons that have the same charge. It's just impossible. And there is no way they'd be sucked to the center. I had fights with all my professors, and anyway, what I'm getting at is I understand this. I'm not talking about things I have no right to talk about. I have every right in the world to make the statements I'm making based on the work that I did. And everything that was written since Einstein talked about the speed of light being consistent was ridiculous, absolutely ridiculous. I did all the chemistry, I did all the experiments, I did, you know, all the principles and constants, and I showed that they're not right. Concentrate on energy of electrons, Schrodinger derived, expressed. They just, nothing I could find was right. X-rays, different spectrums. Light energy, the nature of light. So at any rate, that's my background in it. So I have no reason to apologize for making the statements I'm making. I have every right to make them. And we accelerated light, and this was fought back viciously by physics. You can't see light with a cell phone. Who do you think you are? Well, I don't know. They say I can now. You know, I got interrupted a dozen times, but I really want to be sure you understand the CMOS, which is in these phones, can see electrons and so forth. I asked, can CMOS see muons and electrons? Yes. CMOS imaging sensors, including those in digital cameras and phones, smartphones, can indeed detect muons and electrons. And very, very clearly, as I have shown you in these images here. And this goes back to 2012. Now, I think I went into some detail about this somewhere, but I can't seem to find it. But these were all taken with CMOS, and now CERN is using that. And when I went to University of Geneva, they fought back against it. So did Fermilabs. They all did. But now they realize, and they are using a CMOS as well, because it's absolutely fabulous to see these particles, the energy given off by them. Nothing better. All right, this can get pretty complicated, so I'm going to get very simple. This Yukawa coupling is basically a Dirac, which is a positive and negative. I'm not going wrong with that. I'm not saying anything against that. And it's saying the interaction is developed to model the strong force between hadrons, which do not exist. There's only the black and the white particles. The Yukawa interaction is thus used to describe the nuclear force between nucleons, which they're calling pions, basically, which are pseudo-scalar mesons. They got so many different names, it's just unbelievable. Well, what is a pion? In particle physics, pion is the two particles that are locked together. Now let's get a little deeper into this, and that's as deep as I'm going to get into the chemistry or the physics of the particles, but I'm going to show you why dipole electron flood theory solves all this nonsense. You don't need all these crazy names. You got two particles, that's it. You see this? I found this extremely interesting. This is a CERN, I believe, and this is the base tracks of electrons and the base tracks of muons. So you got your electrons and your muons, which are attached together as photons, basically, and they split at the Venturi, and they're coming in at this very, very low energy. See, low energy showers, and then all of a sudden they come way up like this when they hit the Venturi, and that's the electrons. Those are the energy ones. You get high energy showers, high energy, large shower cones, which is exactly what I showed you. What is this? These are the base tracks of the muons. These are the black balls. They hit and they just bounce back. They don't go. However, they're showing them eventually sort of leaking through. We can do it both ways. We can let them leak through, or we can completely separate them. Watch. Don't forget, this is the high energy showers, the white. These are the muons, the black balls, and they're showing them stacking up and not, they shower early, it says. The muons have earlier shower, yes. At the Venturi, they shower because they're not being allowed through easily. These can just squirt right through, and that's what happens, just like a hose. I mean, almost identical to the nozzle on a hose. It's a Venturi. What CERN was showing was this, where they restrict, and the black bounces back, but some squirts through with the white. Now we can make just the white come through and no black. Can you see the black there? The Venturi is the key. The design of the Venturi will determine how much black gets through and how much white gets through. And now let me show you. All right, I showed you this one where the black gets through, just a squeak of black gets through. Not all of it, but some of it. This one was the acceleration of the light, and literally particles pulling itself out of the wave and exploding basically right in here because it thinks it hit a wall. The reverse wave, as I said before, is concussive against this. It's a push to shove, and it says, whoa, it feels like it hit a wall, because this can hit a cushion and it just goes oof, or it can hit a solid steel wall and go boing. It depends on what it's hitting, how it reacts. It thinks it just hit a wall because this is like a shock wave backwards. And they've been talking about, wow, they can see light going both ways. Yes. It's all the stuff I've been showing. Light is going both ways. Here it is right there. All right, that's a light wave going this direction, and that's a light wave going that direction. So yes, it's quite obvious it goes both directions because it bounces here. And it continues through the slit. And that's what the only reason they can say it goes both directions is because they had a slit, and they let some of it go through and some of it bounce back. Now let's look a little closer at this. So don't forget, we got the concussion here, and here is where the muon shower starts. And the electron shower keeps going. Remember I talked to you about CERN showing it here? The electron shower continues to get bigger and bigger and bigger as it goes through. The muon goes boing and it goes down. Now, we have it not only letting some of it through, but we have it where it lets nothing through. And here it is right here. Coming down, bang. There's not a taste of white, black in here, none, zero. Not a single one. Now, why do we see these black balls? And why? They're all the same size. They are all the same size. And they're trying to sneak back in and catch a hold of the white ones. Now, this is dark matter. Black dark matter, they've never seen it before, because when they explode their stuff, they don't know where it came from. They can just see a whole batch of stuff, and they see some black ones, they see some white ones, and yellow ones, and green ones, and all these kind of different colors. But they don't know where they came from. Well, we know they started as the little black and white particles in the dipole electron photon. Now they're separated. That's a sterile muon. These are sterile. It means all by themselves. And this is sterile, raw electricity. If you put a harvester right there, you could absorb that energy before it got back to the black. All its purpose in life is to be attached to the black. That's the strong nuclear force. And if you had an energy sucker right here, like a solar panel, you suck all that white in, store it or use it. It could be potential energy to be saved, or it could be kinetic energy, just plug right into it and you just take off with it, do whatever you want. And you could have as many of these as you want, basically, in a little lunchbox. They would not give off any kind of dangerous anything. This is just light. Now, if you put your eyeball down in there, yeah, you're going to have a problem probably. But it's unlikely you're going to do that. Plus, you're going to have a box around this thing of whatever has to be put there to keep it from bothering you. Nothing's going to come out of there anyway, I don't think, because these come right back together just like that. And then they become just nothing more than they were when they started, light. It goes in with these, you see these waves? This is the key of it. This is so cool. They come in a wave like that, a little round disc. And then they come back out when they recombine back out as a round disc. Look, this is stuff that excites the hell out of me when I start to realize what I'm looking at over and over. I've been doing this for many years now. Look at this. It comes in this way. That's what light is. You shine a light, and it's a wave. They used to call it particle wave duality. Yes. The particle is in the center and it has a big field around it, so everybody else has their field, they got to get out of the way. So this one coming through is a particle wave, and here it is accelerating, and here it is dividing. Now, what is it accelerating? It's a wave and a particle here. Well, what happens after it comes out of the Venturi? It's been separated. What does it do after that? Well, guess what? It comes back to being the same thing. This is looking into the Venturi. This is like looking into here. We're looking in, and these fields are all coming out at us right here. All right, take your time to think about this. I got my laser going here. Pip, 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 and the particle goes, and it brings a big ball of energy with it, which is the field. It creates a wave. All right, wave-particle duality. All right, now, and that particle is spinning. It's not a floppy wave like this. I'll show you that. I can prove that. It accelerates. It explodes. It's in two pieces now. The black and the white are separated. When they come back together, almost instantly they recombine and they turn right back to what they were before. Only they're a little high energy now. We can see the particles in the fields, but it's the same. Right now they're spinning pretty fast because they just came through that ringer. All right, this is the ringer. Light comes down in a field like this. You have a particle that is the photon, and it spins. And I think I have an idea why it spins. I'm not going to talk about that now. But they do spin. They don't flap like this. Now, if you looked at it sideways, though, you would look like a wave. Because there's a duration to the spin. In other words, it spins 1 time a second, a half a time a second, a third of a time, that type of thing. Here it's spinning 16 times a second. That's the difference in light. That's what gives light its energy. The faster it spins, they're showing it as a wave. Well, they're not waves. They're spins. It's a micro spin, radio spin, infraspin. And it's spinning. But if you look at it like this, you see a wave. I can go along with that. And the faster it spins, the closer the wave becomes. Very simple, basically. And way down here, you're in the red range. And then you go below that, and you're in sound. The wave is nothing more than a vibration of particles. And they sort of bump along. And if they really get whacked, they take off like light. So this is why it separates. This is a drill. Literally a drill. Light spins like a drill. You see that? Talk to any machinist. They'll say, yep, that's a drill bit. Now, the light coming out the other side, like I said, extremely agitated. Get the hell away from me. And they create these, what they call interference patterns. They're not just these little spots. Look at how intricate these interference patterns are. All right? They have no idea how intricate they are. They see these little bumps and they say, wow, look at those intricate interference patterns. Well, that's nothing compared to what light can offer in its smallest form. Now, this other nonsense about quantum entanglement, it's not entangled. They don't come back to the same particles they were before. That's absolutely crazy. Do you think those particles are coming back? These are the black particles that were attached to the white ones. Not a white is all by itself. You think they jumped over there and reattached to the white ones? I don't. Maybe you do. I don't. And by the way, this is literally, and I'm not kidding you, this is fission. The white is separated from the black. That means fission. And that is fusion, because the black comes back to the white and fuses back to the white. And this is subatomic. Nuclear, because these are the same particles that make up the nucleus. Subatomic nuclear fission and subatomic nuclear fusion. Now, when they have atomic bombs, those chunks that are dangerous to us, they're no good anyway. This is what you want, is just white. This is the stuff that gives you the energy. An atomic bomb, they're like throwing hand grenades of these things at you. In other words, when we go through our particle barrier here, we're coming out with these. and they just come right back to being light. So we're never up in their range. They have something that's so enormous, when it blows up, it throws chunks like this everywhere, and those are the killers. The white is the energy. This is what we want. If you wanted a nuclear world of using energy, this is it right here. Using energy out of these is just too much. It creates too much danger. They're too heavy, they're too dynamic, they're too invasive, they're too destructive. We need to stay in this light realm, which is what we did. And then I don't think you can get hurt. I don't think you can get hurt with the light. As long as you don't like penetrate it like a laser beam right on your face, that type of thing. Obviously, this is going to be in something like this, and you could carry that around. It's what it would have is what's called a floating ground, which means when that white particles get stored, they have to come back to ground. So we would have them come back to ground in this shoebox. That's a Geiger counter, old one, but you could have anything you want in that. It's just a mock-up, but you could plug anything you want into there, any voltage you want. You just select what you want, and it would be it would never have any. It wouldn't gain any weight. It wouldn't gain any weight. When you're creating energy, you're just creating energy. It has no weight. So whatever it weighs now, that's what it would weigh as it was doing its job. And you could run that right out of here and just plug right into water pumps and lighting and, you know, emergency stuff and, you know, generators and heaters. And I mean, it would do anything. It could do anything if it increased the energy. And I don't see how you can possibly say that's not an energy increase. And here's what they say from CERN about the increase of energy. I don't know if I showed you this yet, but this is important. All right, I'm going to show you some charts and things from CERN, Fermilab, and so forth. But the key to this whole thing is, if we can take energy and create electron showers, which we can, and we did, and I'll show you we did, this is what happens. Is as the energy comes in a very low number of showers, when it hits our Venturi, or any Venturi, the shower number of particles goes through the roof, because you've got push to shove is what I call it, and it creates showers. Now, what is this? This is the number of particles in the shower giving it what kind of energy. The U means energy, potential or kinetic, it's energy. It comes in with almost no energy at all, and it starts to build energy as it starts to push against each other. Once it hits the Venturi, which is here, right up through the shower, and that's the energy. 3,000 times what it started out as, basically. That's what they're saying. This is not me. And that's if you can create these electron showers. This is the shower maximum layer. When you hit that, you're golden. This is what this is all about. If we can get free energy, the only way to survive this situation we're in is to get out of expanding our atmosphere. We can't do it anymore. It's too much. The Earth can't handle it. Okay, I think earlier I had shown you that we need to get energy, and if we can do it here with these high energy showers way up here. I may have shown you this a couple times, but that's okay. You have to live with that. Showers coming in, and they grow, high energy showers. These are muons. They whack against there and they bounce back. We have ours so that none can get through, and all we have is white showers. And that gives us this kind of energy, which I showed you, I'm sure, before. As it squirts through, that's energy. Max shower energy. And these are max shower particles, the bits, the number of base tracks. That's a lot of energy increase, and that's what they say. And that was not my little diagram, and that's not my little diagram either. But they are looking like they're using our technology, and they're getting into the photon range, but I think they got to stay away from the gigantic chunks. It's too much. They're too big. And we can see these particles. We can see the photons right there. And they have an up and a down spin, and they're a photon. This one's getting ready to flip. The leading charge is the down. This would be a down spin, and it's charging, and it's going to flip. And then the white one will come in the front, the top one will come, and this one will go in the back and discharge. And that's how they spin. As they push through, they charge, discharge, charge, discharge, charge, discharge. That's what makes them flop and spin. Well, actually, they spin this way. No matter whether they're going this way or that way, it doesn't matter. They still spin according to the polarity of the Earth. That's why they call it upspin and downspin. And that I can show too. So now that was the green one. And you saw it going sideways. It was still spinning this way. This one's going totally that way and it's still spinning this way. The red flopped already. It flopped from upspin to downspin. That's the same particle. All right, and it started off here as a neutrino, which it didn't have enough energy to really be seen as a photon. Here it thinks it hit a wall. That's why it's what a photon looks like, all by itself, a photon. Just in the middle of the air. That just normally doesn't happen. They normally have this kind of a look to them where they're, you know, if they have energy, they have energy, but it's not like this. That's energy like it just hit a wall. And the same thing with the green. The green has the same deal because it's coming through here really hot. And then as it slows down, we can see it. The blue is too fast to pick up a whole lot on. The blue is just too fast. This is the red and the green at the same time. You see how easy the red is to push out of the way? And that is the only time I've ever seen him spin barrel roll like this. You see that? That's a barrel roll. It's rolling this way. They do not do that. They stay this way. The only reason this is rolling that way is because this one's pushing it with its field and making it roll. All right, and that's what's going on there. They're the same particles, and they interact. You see some little green bits stuck in with the red. It's the particles are different particles. They're the same particle, but they're different energies. This one sort of throws me a little bit for a loop because I can see bits of reddishness in here, which is right up in here. And we got green coming all over down in here, pushing these, and then it reconcusses way out there. The green much, much more powerful. And I suppose that's why, now I'm starting to understand it. These are not moving as fast as these. So when the click came on, we're looking at a piece so small that you can't imagine how small. These are like a couple of pixels. That's why they're all blocked out like that. And this one here is a full photon. And so are these. But you can't see them. It's just they're too slow. So you're seeing, just a little glow as it goes by. And these you're seeing as actual photons. I hope that makes sense to you. It took me a while to sort of home in on that, but I believe that's what we're seeing there. But it's quite obvious how much more energy there is than the green than the red. And I believe it's going, actually, I believe it's going faster. I think it's going faster. That's the only thing I can take from it. But I'll tell you one thing, the red is going to slow down a lot quicker than the green. And the blue, the same thing. Blue is much faster than all of them. So we've got a lot of thinking to do here, but they're proving my point. Here it is right here. Muon neutrinos creates a sterile muon. The electron neutrino attached to it, which is the white one, creates the electron showers. That's it right there. That is it right there. Now they're using Cherenkov radiation from some destructive, nuclear source. We don't need to do that. We just use light. This is off-the-shelf stuff. This can be implemented in days, literally. And I need somebody to pay attention. It's been 10 years. And I'm blocked literally at everywhere in the physics world because they want to work with gigantic machines that are kind of expensive. And I understand what they're doing. But if this is the particles that make up the nucleus, and it is, they're all made out of the same particles. They're all made out of these dipoles. These two particles. The gluons. photons, and then the next stable is the 1839, which is a proton. And that would be basically hydrogen. When hydrogen explodes, all those particles take off. And hydrogen is explosive. So because they got to break down to light and heat, you know, they're going to break down into the dipoles, and they're going to break down into photons and concussive forces. But they're going to, each one of those is going to go on its own. That's why hydrogen is so explosive. And this is the whole thing. It's a 5-minute read, basically. And a kid can understand this. These are the only two particles that exist. You put them in a ball like this, and it comes a proton. Now, you add a few extra, it becomes the isotopes, the different isotopes of particles. So if you have an atom that's stable at a certain number of particles, and they only become stable at a certain number, there's a locked-in stability of almost like a vibration of the fields sort of meshing together and contorting so that they get pretty solid, and they say, we don't want any more in here. We don't want to lose any. Everybody's good. Don't take any more on, and don't give anybody up. But you want some to sneak in here. Some will. They're called isotopes. They have what they call... All right, here's what they don't understand. Isotopes, an isotope is one or two or more forms of the same chemical element, have the same number of protons, but different number of neutrons. That's just not correct. They just have more and more dipole electrons. A neutron is nothing more than a stable, because it has the same number, neutral number. So instead of 1839, which wants to give one up to become stable, or take one on to become stable, it has to be an even number. Neutrons are just even numbers. So they're saying that each one of these, like phosphorus, it's thousands and thousands and thousands of variations of phosphorus, and they still call it phosphorus. But they say, well, it's an isotope. They can't explain isotopes. There's no way they can explain isotopes with the standard model, none whatsoever. And they can't explain dark matter. They can't explain gravity. They can't explain the speed of light. They can't explain the mass of protons. Of photons. They can't explain the weight of the particles. They can't explain their dipole nature and how light is literally made of two dipoles.